Hi everyone, I'm Marin and I'm here to present my topic titled Compliance Checking for Construction Project Data with Linked Data, done under the supervision of José Granja, José Carlos Lino, and the company Neonex Technologies, and the Matthias Bonduel as a tutor in the company. So to firstly, okay, as it usually happens. Okay, so firstly, to give a little bit of an outline towards the presentation. This presentation is done in the context of digital building permitting. Digital building permitting is quite a popular topic, and a detailed overview is available in the thesis itself. The most relevant research made was that the building design process is generally very complex and fragmented. And currently manual compliance checking is done for digital building permitting. However, it usually results in low accuracy and high cost, specifically for the investors, and also with a long waiting time. Currently, only 27% of economies of countries use a digitized submission process. Generally, OECD is leading with 48%. However, that's still relatively low. Automated compliance checking, or ACC, has been researched for over 50 years, and it can be kind of considered as a holy grail of computer integrated construction. Significant uptake happened in the last 7 years. It somehow correlates with the increase of adoption of digital representation of buildings and geospatial data across the world. And it's generally automated compliance checking is a complex and a multi-factor problem. It consists both of technical and non-technical factors. This research will obviously deal with the technical part, more specifically how to deal with the fact that not only BIM data is needed for a successful digital building permit, but also other data such as GIS data, some kind of metadata about digital permits, and so on. So there are currently several notable efforts in the EU, so the research is quite relevant. Firstly, there is the DigiPlace project that finished and established like a base layer of a framework. The EU Net for DBP is an association of all relevant stakeholders aiming and pushing for digital building permit. And the most relevant currently are the 3 Horizon Europe projects, Check DBP, DigiChecks, and Accord, sister projects aiming to have each kind of their own view on this complex topic. So generally, from a technical side, relevant findings are that the technological ideas that shape the outline of this research are well accepted in practice. They are developed in at least 2 out of these 3 Horizon Europe projects. Technological solutions generally should be based on open standards, should be easy to use as possible, to take into account the specifics of building permitting process that mostly deals with public data, sensitive public information, and data that needs to be stored for a long time. And generally, taking into account there's many stakeholders throughout Europe, there's very little chance for a one-fits-all solution. And for mass deployment of digital building permitting, flexibility and customization of workflows is key, and that is a good use case for application of semantic web technologies. So to check what semantic web technologies are, that is basically a set of standards that can be seen here on the right. And these standards aim to make data on the internet machine readable, and also in the next step, machine understandable. Information is organized simply by defining the meaning of each of the objects and the relationships between them. What is a little bit different in these semantic web technologies is that instead of creating and encapsulating very big standards, these semantic web technologies generally try to find ways of interconnecting data sources and standards without them directly translating from one into the other. And these semantic web technologies are quite big, so there's various standards. A smaller subset of these standards that only deals with data publishing, that doesn't deal with concepts such as trust, security, and proof. is called linked data. So this linked data is considered in the scope of this thesis. And finally, where linked data comes into connection with BIM is the new EN 17632 standard for building information modeling, semantic modeling, and linking. It's a newly published standard explaining how built environment organizations should apply linked data. It consists of two parts. So firstly, there is a generic top-level construction ontology. And secondly, there are guidelines about generic modeling patterns that explain how BIM data can be converted into such a standard that's compliant with the EN 17632. At the time of beginning of the research, fully the ontologies from the EN 17632 were not available online. Therefore, the Dutch predecessor NEN 2660 is used with the idea that the newly published ontologies will differ very little from this Dutch predecessor. Okay, so now it's important to see what the research outline of the thesis is. And it's very simple. The goal is to see how IFC can be converted, can be expressed in a way that's compliant with this more generic ontology, EN 17632, and in the scope of digital building permits that would enable connection of BIM models to other information models such as GIS, electronic document management, systems engineering, monitoring and control, some metadata about digital building permitting. So basically to enable us to be more flexible with our digital building permitting process. The planned process is on a high level quite simple. Firstly, a so-called object type library is connected from the IFC and from the EN 17632 ontology. This gives us kind of a foundational terminological layer of the whole process. Secondly, to instantiate this terminology, IFC step files are parsed and parsed in a way that they create an object type library compliant dataset that can later be queried and checked for validation. And finally, using the shapes constraint language or shackle, the language that enables validation of such linked data datasets, it is the goal to assess how local, national, or EU regulations can be converted in these shackle shapes to validate linked data datasets. So on a high level, again, firstly, the IFC OWL version of the IFC data model is loaded. So the OTL is established, stored in a triple store. Secondly, specific IFC files are parsed, stored in a separate triple store. Then two of these are merged into a so-called data graph. Shackle shapes are done in the third step, stored in a separate shapes graph. And finally, validation is done by checking data graph against the shapes graph. And the validation process results in a validation report stating that our data conforms, or if it doesn't, where the error is. So firstly, the taxonomy. So the classes are analyzed and an object type library is created out of these classes. Basically, the goal is to connect the higher level generic NEN 2660 or EN 17632 concepts with adequate IFC concepts. So basically saying that some kind of an IFC concept is a subclass of this very generic ontology. This is firstly done by loading the IFC OWL into a web tool called GraphDB by OntoText. Then the querying language Sparkle is used. An example of a Sparkle query is here. And what this query results in is basically this table, as can be viewed in GraphDB, saying each of individual IFC classes is a subclass of some kind of a higher IFC entity, and each of these classes may contain or may not contain certain IFC predefined type enumerations. What's more important, these are not only shown in tabular forms, these can also be returned directly in code as JSON objects. So these JSON objects can be used in the rest of the code. And this was done with JavaScript. So basically, JavaScript code was developed that enables creating graph database such as this one, which basically shows this thing here. So saying, for example, that some kind of a covering insulation class, which would be a bottom level predefined type class, is a subclass of a covering. Such covering is a subclass of a building element, and this building element is a subclass of the non-discrete object, which is then implicitly a subclass of all of these non concepts. The same thing is done with all of these other concepts, such as the spatial ones, saying, for example, that an internal space is a subclass of space. This space is a subclass of a spatial element. And then again, this spatial element is a subclass of a non-concept spatial region. While IFC OWL is not directly used, instead a separate OTL namespace was created. The IFC ontology, IFC OWL ontology maintains connectivity with our new OTL ontology with the RDFS-C also predicate, so there is a direct correlation between one and the other. Secondly, after establishing this taxonomy, attributes were needed to be analyzed. And there's two ways of property modeling prescribed in the new EN 17632 standard. Firstly, there is a way where qualitative attributes are expressed, saying just that a certain object can have a certain color, can be placed at a certain time, and such so-called qualitative properties, and so-called quantitative properties, which are then level 2 properties, saying that some kind of an attribute has a unit and an actual value. They need to be separated into distinctive nodes. So the IFC OWL was queried then, firstly for level 1 attributes, and then depending on the results, a mapping table needed to be done to replace the IFC concepts with the concepts prescribed in the EN 17632. And an example of such level 1 attributes is here, saying that a building element class needs to have a global ID, a name, a description. All of these need to be of a type string as prescribed here, and they either need to be required, so a count of 1, or these need to be optional, so count either a 0 or a 1. Level 2 states that a separation is made where, for example, an overall width attribute has a separation of overall width unit that has a certain path of a has unit from the NEN 2660 ontology, and an overall width value which says that the path is the RDF value again from the EN 17632 ontology. And in this way, very briefly, we created this terminological layer as a base layer, and then this base layer needs to be instantiated. On test use cases, 3 BIM models were used. They were developed in BIM A+. 2 module and these were used because it was sure that these models were done properly, that the IFC files were valid and adhere to, let's say, the highest of standards. So the workflow is visible in the let's say BPMN modeling rules. They're available in the dissertation, so I won't go through it individually for the sake of time. What they result in is instantiation of each elements represented by the GeoIDs. they are done classified as types depending on the IFC classes that were established in the step before. The same was done if such classes were done manually as user defined in a certain data sets. So there's certain, let's say, flexibility here. And again, relations were respected, relations for aggregation and spatial containment, saying, for example, that each of the projects needs to have a site needs to have one or more buildings, and a building needs to have one or more building stories. A building story contains one or more spaces, and each space can contain more elements, such as this one, for example, contains a pipe fitting. This way, the relations of spatial containment and aggregation were expressed in compliance with the EN 17632. The same was done for attributes. Again, I won't go too much into details. The process that is visible here was done in the code, so using JavaScript. What it results in is that each of the objects that has a type here also has level 1 attributes, and also has certain level 2 attributes that have their values, and again, the units aligned with the EN 17632 ontologies. Finally, the test was done by checking with the IFC to LBD converter that already exists. And basically, the results were very similar. The data sets produced as a scope of this thesis only have one more node, and that node is the IFC project node, which was created manually in the JavaScript code developed as a part of the thesis, whereas the IFC project doesn't get parsed in this IFC to LBD parser that was developed before. Finally, these shackle shapes were tested to see if it is possible to validate data sets for compliance with certain regulations. And it indeed is. There are multiple ways that can be tested. For example, existence of attributes can be tested. So on, let's say this belongs more onto an object type library level, for example, it can be prescribed that each of elements needs to have at least one and at most one global ID. And if there exists a certain element that doesn't have an ID, errors come up saying that there's something wrong with these data sets. Value constraints can be checked both for existence and also for certain values. For example, if accessibility is assessed for compliance, it can be said that a door needs to be at least 2,400 millimeters high or 1,000 millimeters wide. And if a certain door doesn't comply, an error shows up saying that there's something wrong with this data set. And it also points specifically to the element in the database. And finally, relational constraints showing that some kind of spaces need to have at least some kind of elements. For example, a toilet needs to have at least one wash basin in its containment, and so on, can be expressed. So it is definitely proven that quite a lot of validation can be done with shackle. So connection of standardized data models using these semantic web technologies was definitely proven possible. Compliance checking is also possible. And again, parsing the project data using IFC.js, also in combination with other libraries for graph databases such as Zazuko, can create linked data versions of project data. Throughout the process, some remarks about the IFC structure were made, and these can be considered as an important contribution because they also go a bit wider than just the linked data world. For example, consistency in enumeration naming is needed. Some predefined type enumerations have underscores, some don't. And that makes it quite hard to parse these because there's not a simple unified rule that encompasses all the enumerations. So in the thesis, a list of these enumerations that do have underscores is made, so that can maybe be used in the next versions of the IFC to, let's say, fix this issue. Some additional questions appear that weren't answered, such as how to merge data from several discipline models into a federated model. For example, if a toilet is checked for existence of a wash basin, sometimes the room, the space of the toilet, is actually in an architectural model, but the wash basin element itself is an MEP model. How to make sure these are aligned on a linked data level. There are several approaches. For example, spatial computation approach, that's quite heavy. There's also linked data approach that on a graph database level connects these objects. But then again, there needs to be a bit more thorough investigation, what's better, what's easier. And definitely quality of the IFC files exported from proprietary tools is questionable, such as if a type is predefined, then an object type needs to be done according to formal propositions of building smart. An example of this is shown in an open source IFC native modeler that shows how it should be done. And for example, a certain proprietary tool, very well known and widely used, doesn't export according to the rules as prescribed by Building Smart. Then again, these are the certain limitations that the process is very dependent on the quality of the IFC files. So an EIR, exchange information requirement, should be done to prescribe in detail how modeling should be done to ensure compliance with the workflow. And again, the IFC schema itself still lacks some important concepts, for example, for tunneling or renewable energy, but these concepts are being developed as we speak, so hopefully next versions of the IFC schema will have these important concepts. Regarding the future research proposals, there's many proposals considering that the application of semantic web technologies is getting increasingly popular, both in academy as well and is in the industry, because it's very flexible and can be a solution to connect different type of heterogeneous data sources. So future research proposals can go horizontally, so we can investigate the interconnectivity between these two standards on a deeper level. Currently, IFC OWL only contains attributes, so no properties were analyzed. And also a question is what to do with custom properties and property sets. Should some kind of string similarity be used? Only a small subset of the schema was connected. Newly, similar workflows should be investigated for MEP connections or objectified relationships, for example, the ones regarding materials. Additional versions of the schema should be converted. Most importantly, it would be the IFC2X3. And the EN 17632 continues to be published, so the new published document should be taken into account when continuing the research. Also vertically, seeing how the stuff developed in this thesis should be used to develop end-to-end functionalities. For example, building proof of concept applications for digital building permitting that have a user interface, that have automation of shackle shape creation. We can see how linked data should be used in asset management, in connectivity with Internet of Things. And also, this research definitely won't end here due to some future projects that are already, let's say, discussed and are on the way. So thank you for the attention.